Hello bachcho and welcome. Today we're going to tackle a very interesting topic from our unit 13, which is nuclei. We'll be looking at atomic masses and what the nucleus is actually made of. Now don't worry at all. I am going to make it bilkul simple so you can remember it easily and score full marks in your exams.
So here is our game plan for today. We'll start with a little mystery you can find right in your own house. Then we'll solve a very curious case of some missing mass. After that, we'll learn the proper language of the nucleus, just like the textbook wants us to. We'll put all the pieces together with an example, I'll warn you about some common exam mistakes, and then we'll wrap it all up. Cello, let's begin.
Okay, let's jump right in. And to start, I have a question for you. Something you see every day but maybe never really thought about. You know that small white box on the ceiling? How does it magically know when there's smoke in the room? Is it some chemical sensor? Well, the answer, believe it or not, is pure nuclear physics, exactly what we are going to study today.
You see, inside that little detector, there's a tiny piece of a radioactive material called americium-241. Now, this thing is constantly firing out little invisible particles. As long as these particles are flowing, a small electric current is on. But the moment smoke enters the detector, it blocks these particles. The flow stops, the circuit breaks, and beep, 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 the alarm starts screaming. So you see, nuclear physics is quietly working to keep you safe at home.
So that was just a little hook to get you interested. Now let's get to the real heart of today's lesson. I like to call it the case of the missing mass. It's a proper puzzle. Listen carefully.
To understand this, let's just imagine a simple situation. Let's say there are two people, and each person weighs exactly 70 kilograms. Now they get married and decide to stand on a giant weighing scale together. What should the total weight be? 70 plus 70, 140 kilograms. Simple maths, right? But what if I told you that when they stand together, the scale shows 139.5 kilograms? Where did that half a kilo just disappear? It's a mystery.
Well, believe it or not, something very similar and even more dramatic happens inside the nucleus of an atom. If you take all the protons and neutrons, weigh them separately, and add up their masses, that total is always more than the actual measured mass of the nucleus when they are all packed together. So where does that missing mass go? It's not lost. It gets converted into a tremendous amount of energy, an energy that acts like a cosmic superglue, holding the entire nucleus together. And we have a special name for this, binding energy.
Now this idea is really amazing, but to score marks in our exams, you know how it is, we have to use the official language of physics. So let's quickly go over the exact definitions from your NCERT textbook. First things first, the units. You know, the mass of a single proton is so incredibly tiny, using kilograms is just not practical. It's like measuring the length of an ant in kilometers. So we use a special unit called the atomic mass unit, or simply U. And by definition, 1 U is exactly 1/12 the mass of a single carbon-12 atom. This is our gold standard for all calculations in this chapter. Next up, how do we write about a nucleus in shorthand? We use this standard notation. X is just the symbol for the element, like AU for gold. At the bottom, Z is the atomic number, which is just a count of the number of protons. And at the top, A is the mass number, which is the total count of protons and neutrons together. So if you see 197.79 AU, it means gold, with 79 protons and 197 total particles in the nucleus. Simple. And to find the number of neutrons, just do A minus Z.
Now for a very important word, isotopes. Isotopes are basically siblings. They are atoms of the very same element, which means they must have the same number of protons, the same Z, but they have a different number of neutrons. A perfect example is carbon-12 and carbon-14. Both are carbon because both have 6 protons, but one has 6 neutrons and the other has 8. Chemically, they behave the same, but in the nuclear world, they are quite different.
And this brings us to 3 terms that are a favorite in exams. Just remember this. If the Z is the same, they are isotopes. If the A, the total mass number, is the same, they are isobars. And if N, the number of neutrons, is the same, they are isotones. Please remember this difference. It's an easy place to get full marks.
Okay, enough of theory. We've learned the language, we understand the words. Now let's get practical. Let's use these ideas to actually calculate that missing mass with a very simple example.
So let's calculate the mass defect for a helium-4 nucleus. We know it has 2 protons and 2 neutrons. Step 1. We'll find the expected mass. We'll just add the mass of 2 protons and the mass of 2 neutrons. Step 2. we look up the value for the actual experimentally measured mass of a complete helium-4 nucleus. And finally, step 3, we just subtract the actual mass from our expected mass. The result is our missing mass.
And what do we find? The difference is 0.02928 atomic mass units. I know, that number looks incredibly small. But don't let that fool you, because thanks to our friend Einstein, we're about to see that this tiny bit of mass turns into a huge amount of energy.
So here it is, the official formula you must write in your exam. Mass defect, or delta M, is the mass of all the protons and neutrons added together minus the actual real mass of the nucleus. And this missing mass, this delta M, is what gets converted into binding energy, all thanks to the most famous equation in all of science, E equals mc squared.
All right, now for a very important section. Let's talk about some common traps, what I call the silent killers, that can silently steal marks from your exam paper. Many students make these simple mistakes.
First big mistake, students often write that mass is lost or destroyed. Are baba, no. Be very careful with your words. In physics, mass is not destroyed, it is converted into energy. The total amount of mass and energy together is always conserved. It just changes its form. This is a crucial point.
The second common trap is to think that heavier is always better, that a bigger, heavier nucleus must be more stable. This is not true at all. In fact, the most stable nuclei are the middleweight champions, right around iron. Nuclei that are very heavy, like uranium, are actually less stable. They are kind of bloated and ready to break apart. That's why they're radioactive. Stability is all about binding energy per nucleon, not just the total weight.
Whew! We have covered a lot of ground. So, before we finish, let's quickly summarize the absolute most important points that you must remember for your exams.
So here are your key takeaways. Number 1, the nucleus is made of protons and neutrons. Number 2, a complete nucleus always weighs less than the sum of its individual parts. Number 3, this difference in mass, the mass defect, is what turns into the binding energy holding it all together. Number 4, an isotope means same number of protons but a different number of neutrons. And finally, number 5, always remember the standard notation AZX.
So, we have figured out that this mysterious, missing mass is the secret source of the energy that glues a nucleus together. But that leaves us with an even bigger, more exciting question. Just how much energy are we talking about? How can this tiny speck of missing mass be enough to explain the unbelievable power of the sun or the devastating force of a nuclear bomb? Well, that is the question we will answer in our next session when we explore binding energy, fission, and fusion.